All right, so hello, my dear friends. I hope you're all doing well. My name is Benatang Patun, and welcome to the channel Classroom, where we learn together. So, there's been a long gap. I know, okay. So, what happened was that, well, first of all, exams were going on. So, because of the exams, I got very busy being the class teacher. I had to prepare the results and then I have to distribute the results. So, well, that is my work, but that got me pretty much occupied. Paper checking, result preparation, it takes a lot of time. So, because of which I could not get the time. But now everything has been done, the results have been distributed. So, I am more free now. Plus, there were some works which need to be done, because of which I did not get this time to record the class also. So I apologize for that. Now, hopefully, by the grace of God, things are back to normal. So I'll be frequently uploading. Okay, I'll go back to my previous state, which is I upload frequently. So that's what I will do. Okay, so well, it was not easy also. Okay, it is always there. If I don't upload, I know that since it is my duty, okay, I have taken this moral responsibility to upload. So if I don't upload it, then it also haunts me. So I am happy that today I am finally able to record it. And interesting fact, the topic for today's has been written here. It's going to be Fleming's Left-Hand Rule, but this has been written maybe more, or like it has been here for more than a week. So that's how it was. Okay, I got ready to record, but then never got the time. So this is what was happening. Okay, the background story of what I was doing for the past few days. So that's it. Okay, so now let's continue learning. So that this will be our topic today. Okay, Fleming's Left-Hand Rule, a very important rule and a very easy rule. Okay, which helps you. Now, why do we study Fleming's Left-Hand Rule? We study Fleming's Left-Hand Rule because it helps us find the direction. I repeat, the direction of force acting on the current carrying conductor. So Fleming's Left-Hand Rule helps you find the direction of force acting on the object, or acting on the current carrying conductor. So remember, we study Fleming's Left-Hand Rule because it helps us find the direction of force acting on the current carrying conductor. So let us do a quick review because there has been a long gap. In the previous class, we were learning about force acting on a current carrying conductor placed inside an external magnetic field. So we had a magnet. I think I have the magnet with me. Yes, it's still here. So this was the magnet which I used to explain in the previous class. And this was the current carrying conductor. So when current was made to pass through this wire, this is a magnet. It has got its own magnetic field. But now, when current passes through this through this metal wire, okay, this also produces its own magnetic field. So two magnetic fields are interacting. So I told you, when two magnetic fields interact, it could be a force of attraction or a force of repulsion. So it could be a force of attraction, or it will be a force of repulsion. Okay, and we have discussed this in detail. So Fleming's Left-Hand Rule, in continuation to the previous video. Now, this video and the previous video, they are interrelated. Okay, they are interrelated. Fleming's Left-Hand Rule will help you understand better, okay, the previous video also. So, and we should study Fleming's Left-Hand Rule after watching that video. So if there's any one of you who has not watched the previous video, I will recommend you to watch the previous video, because you will understand better if you have a knowledge of the previous video. So using Fleming's Left-Hand Rule, we will be able to find the direction of force which acts on the current carrying conductor. This is the reason why we study Fleming's Left-Hand Rule. We'll be doing a lot of examples, okay, where you will understand better. So let's write down the statement. There's a statement here which you should write down and you should study, because it is asked in exam. So take out your notebook, grab a pen or a pencil, and then write down the statement. So let's get writing. So first we'll write down the statement. The statement reads, stretch your forefinger comma center finger and the thumb mutually perpendicular to each other such that the forefinger what should I write? Points in the direction of magnetic field. Let me underline this, comma, the center finger indicates the direction of current and the thumb gives the direction of force, and the thumb gives the direction of force, bracket, you write, motion. So this, my dear students, is the statement of Fleming's Left-Hand Rule. So I'll move to the side. You kindly pause the video and then you copy down this. So assuming that you have copied it down, now let us understand this rule. Very easy rule. Since this is left-hand rule, let's utilize our left hand. So let me stand here. Now the statement reads, stretch your forefinger. So I have currently made a fist. The forefinger is this finger. Stretch the forefinger, I have done it. Center finger, so this is the center finger, okay? And the thumb. So I have to utilize the thumb, the forefinger and the center finger. Such that, okay, and the thumb mutually perpendicular to each other. So these three fingers, they are mutually perpendicular to each other. So don't mind my thumb. Unfortunately, my thumb cannot be perpendicular, okay? I have to hold it like this way, but my thumb is not, naturally it won't go like this. So or else if it was like this, then perfectly, okay, they will be perpendicular, but I cannot do it, okay? If you can do it, then good. Let me see, who can do it? Kindly tell me who can do it. Yes, who among my students can do it? All right. If you can do it, that means that you are blessed, okay? You are a special child, okay? Unfortunately, okay, I'm not that blessed, okay? No, we're all blessed, okay? We're all blessed. God loves us all, so I'm also blessed, okay? But then, okay, unfortunately, I'm not able to keep my thumb perpendicular, exact perpendicular, but it's all right, okay? So this is the orientation. Then now each of the finger, they represent one or the other thing. So the forefinger points now, okay, they are mutually perpendicular to each other such that the forefinger, this finger points in the direction of magnetic field. So this forefinger, what does it indicate? The forefinger, it indicates the direction of magnetic field. So the forefinger, it's pointing away from my body, it's pointing that side, okay? So it's facing away from my body. So the forefinger indicates the direction of magnetic field. So the forefinger will give you the direction of magnetic field. Currently the magnetic field is in this direction, okay? Then, and the center finger indicates the direction of current. So the center finger, this one, okay, it indicates the direction of current. Well, if you look at this, okay, this center finger is pointing towards you. It's pointing towards you, okay, it's pointing towards you. So the center finger indicates the direction of current, okay? It is telling me where the current is going. So the current is heading towards you, okay? The current is heading towards you. The magnetic field is heading towards this side, okay, away from my body. And the thumb gives the direction of force. Then the direction of the thumb gives the direction of force acting on the object or the conductor. Okay, so the thumb is pointing upwards. That means the force acting on the conductor will be upwards. Okay, so the force acting on the conductor will be upwards. Now, Fleming's left-hand rule we study because of this, because we want to know the force acting on the current carrying conductor. And see, the thumb, okay, the thumb will help you determine the force acting on the current carrying conductor. All right, so we will be doing some examples there. You will know, okay, you will know. So no need to worry. With some examples, you will, okay, easily you will master it. So don't worry. So remember this, my dear students, that this is the force, this is the magnetic field, and this is the current. We can also remember this as father, mother, child. So F for force, the force you can remember as father. Then magnetic field, it will be mother. And the current, it will be child. Okay, so some students, they also remember it like this in the exam. So this is the force, so father, magnetic field, mother, current, child. Father, mother, child, force, magnetic field, current. So if this helps, you remember it like this. All right, so now let's do some examples so that you will have no doubt. Examples are very important. Laws and statements, with examples, we understand better. So we have to practice some examples. So let's practice together some examples. Now, let's say the magnetic field is in this direction. So these are the magnetic field. Let us take two examples. So let me draw another one here. What are these? These are the magnetic field. So this is the magnetic field. Now, let us bring a wire. So let us bring a wire. So let us bring a wire. So this is a wire. Now, let us bring current also. So let us bring current. Now, let's say current is flowing upwards. So let this be the direction of current. So current is flowing upwards. The question is find F. You have to find the direction of F. Okay, you have to tell me the direction of force acting on this current carrying wire. So using Fleming's left-hand rule, let's find out the direction of force acting on this current carrying wire. So we have magnetic field and we have a current carrying wire. So this is the external magnetic field, and this current carrying wire produces its own magnetic field. So two magnetic fields are interacting. So a force will be acted upon this current carrying wire. So there is a force acting on this current carrying wire, and I want you to find the direction of force acting on the current carrying wire. How do I find it? Very simple. Use Fleming's left-hand rule. So let's use Fleming's left-hand rule. So everybody position your hands. All right, everybody did? Yes, everyone? Done or not? Okay, so let's do like this, and let's correctly orient our fingers and find the direction of force acting on this current carrying wire. Okay, so magnetic field is pointing away from my body, so it's in that direction. So this is the right orientation. Magnetic field is going like this. Okay, this forefinger indicates the direction of magnetic field. So the forefinger is in the right direction. Then current is going upwards, so this is wrong. So I have to realign my finger. So how do I do it? Simple. Okay, so now the center finger, which indicates the direction of current, okay, is correct. Current is going upwards, so my center finger is also pointing upwards. So current has been aligned. Magnetic field has also been aligned. Then the thumb, Okay, the thumb will give the direction of force acting on this wire. So the thumb is pointing inwards. The thumb is pointing inwards into the whiteboard. So force acting on this current carrying wire is inwards. So that's how you find the force acting on the current carrying wire. So easy. So direction of force is inwards. So the force acting on the current carrying wire is inwards. How did I find it? I found it using Fleming's left-hand rule. Easy. Still confused? Don't worry. One more example. Okay. So we will take another example. So let's take another wire. So this is the wire. Now, previously the current was moving upside. Now let's change the direction of current. Let's make current go downwards. So let's make current go downwards. So the direction of current has been changed. Magnetic field still in the same direction. Question: find the force, the direction of force acting on this current carrying wire. So we have to find the direction of force acting on this current carrying wire, which is placed inside an external magnetic field. Now, how do we find it? Fleming's left-hand rule. So let's position our fingers again. Everybody do like this. All right, okay, done. So let's do. So again, let's start with the forefinger. The forefinger should point in the direction of magnetic field. It's pointing correctly. The center finger should point the direction of current. So this is wrong. This is wrong. Okay, current is going down. That means the center finger should also point down. So is this the right orientation? Yes, this is the right orientation. Okay, so current is going down. Isn't it? Current is going down. Magnetic field pointing in that direction. Correct. Now, what will give the direction of force acting on the current carrying wire? The direction of thumb will give the direction of force acting on the current carrying wire. So the thumb is pointing outwards. The thumb is pointing towards you. Isn't it? That means it's outwards. Okay, so the force acting on the current carrying wire is outwards. The thumb is pointing outwards. The thumb gives the direction of force acting on the current carrying wire. So the force acting on the current carrying wire in this case is outwards. How did I know? Look at my thumb. The thumb is pointing outwards. It's pointing towards you. So the force acting on the current carrying wire in this case is, what is it, my dear students? Anyone? Raise your hand and tell me. What will be? Yes, outwards. Okay. See? So easy. I told you, nah? It's so easy. So I hope you understood. It's very easy. Okay. So all you have to do is align your forefinger, center finger, and that's it. You will automatically, okay, the thumb will automatically align itself. Okay. And then you will be able to find the direction of force. So make sure that your forefinger and the center finger, they're aligned properly. So read the question thoroughly and make sure that, okay, you align your forefinger and the center finger correctly. Then I assure you, you will always get the correct answer. All right. So now moving ahead, let's go to the next topic. The next topic will be force on moving charge in external magnetic field. So that will be our next topic. So let's continue with our next topic. Force on moving charge in external magnetic field. This is our next topic. Okay, now we are going to learn about force acting on a moving charge when placed inside an external magnetic field. Now, how many types of charges are there? Let me ask you this question. How many types of charges are there? Charge. Since our topic is about charge, I want to know how many types of charges are there. Correct. There are two types of charges. we have positive charge and we have negative charge. Yes or no? So there are two types of charges, positive charge and negative charge. So my question, the next question that I have is, okay, very important question, and you have to answer with this question. Will a moving charge produce magnetic field? Question mark, question mark, question mark, 3 question marks, because it's very important. So the answer I want you to give me, it's just a simple yes or no question. So will a moving charge produce magnetic field? My dear students, who will give me the answer? Yes. Tell me the answer. Yes. All right. So correct. The answer is yes. A moving charge will produce magnetic field. Okay. Now, if there is any doubt, then let us elaborate a little bit on that. So remember this, that a moving charge will produce magnetic field. So basically what I'm telling you is that if a charge moves, then it will generate its own magnetic field. That's what I'm telling you. Okay, when I say yes, I'm telling you that when a charge moves, whether it's a negative charge or a positive charge, when it moves, it will definitely generate its own magnetic field. So this is magnetic field, this is magnetic field produced by the moving charge. So when a charge moves, it will produce its own magnetic field. So if there is any confusion, if there is still any confusion, then let me give a slight explanation. So let us assume a wire in which current is flowing. So current I is flowing. So this is a current carrying wire. You all agree? Yes, we all agree. So a current carrying wire. My next question here is, does a current carrying wire, or will a current carrying wire produce magnetic field? The answer is yes. A current carrying wire produces magnetic field. We all know that. Okay, if the wire is straight, then it will produce circular magnetic field. If the wire is a loop, then it will produce straight magnetic field. We know these things. We have studied in the previous video. Yes, and you are all smart, so you know that. Okay, so the answer is yes. Now, moving ahead. Okay, stay on the track. Okay, we're coming to this one where I'm gonna make you realize that, oh yes, okay, there should be no confusion. Now, what is current? Isn't the flow of electrons current? Isn't the flow of electrons current? Okay, what actually is current? Current is produced because of flow of electrons, is not. It is because electrons are moving, okay, that we get current. So we know that, okay, we know that the battery pushes the electron, the free moving electron. Okay, the free electron is being pushed by the battery, and it is the free electron which moves in the wire which actually makes current. So who is moving? An electron is moving. What charge does an electron have? An electron has a negative charge. This fellow, isn't it? An electron is this one. So an electron has negative charge. So what actually is moving? A negative particle is moving. A negative charge is moving. Yes or no? Yes. So electron, which is a negative particle, is moving in the wire. Okay. And when this negative electron moves in the wire, we call it as what? Fill in the blanks. Yes, we call it as current. Okay, that makes this wire a current carrying conductor. And you agree that a current carrying conductor produces magnetic field. Okay, so if you agree that a current carrying produces magnetic field, you should know that what is flowing in the wire. An electron is flowing. What is an electron? An electron is just a negative charge. Okay, so that confirms, this confirms 100% that when a charge moves, okay, when a charge moves, it produces magnetic field. So it could be a negative charge, it could be a positive charge. Okay, so when a positive charge moves, it will also produce magnetic field. When a negative charge moves, it will also produce magnetic field. When both the types of charges move, it will definitely produce its own magnetic field. Okay, so remember that a moving charge will definitely produce magnetic field. I hope that's clear. Okay, so let's erase this now that you have understood, and let's continue further in the discussion. But before that, I'll give you a table. Now there are three types of particle. So copy down this table. So I'll give you a table on the types of particle. So there are three types of particle. What are those particles? Let's write them down. Let's write them down. Let's write them down. Let's write them down. My English is getting worse and worse. First, it's my spelling, and now my English is also getting worse. Okay, we are supposed to get better with time, but then I feel like the person who talks the most at one point in their life, I think that person will lose the language also to talk. Now, like, I think this is what happens to. This is the paradox of the world. Okay, the most talkative person may become the most silent person. Okay, it may shock you. The world runs on reverse order sometimes, and I strongly believe that. Okay, so a talkative person, after some few years, you will see a change in them. They will become very quiet, and then a very quiet person in the beginning can become very extrovert, and then you will see him or her, okay, performing on the stage and becoming very, like, not shy at all. So okay, the world is quite opposite. So if today you are shy, and if today you are shy and nervous, I assure you tomorrow you will be bold, okay, and you will be there taking the lead. And those who are active today and all that, be very careful, because tomorrow the cards may reverse, and then you and I, okay, anybody, we may be, okay, we may not have that zeal anymore. So okay, we have to know this. Okay, so the world we live in is sometimes it reverse happens. So that's what I'm afraid of. Okay, I'll talk, but then if I lose my sense of grammar and my sense of spelling, then what good will I talk? Is it not? So I like to talk, but then my talk should make sense. That's what that's how I should talk. So let's continue. So write down here positive, here negative, and you write down here neutral. So these are the three types of particle. We have positive particle, we have negative particle, and we have neutral particle. So example of positive particle, we have proton. Negative particle, we have electron, minus, and neutral particle, we have neutron. For proton, plus, because it's a positive particle. For electron, negative, because it's a negative particle. For neutron, what do I write? Neutral, no charge, so 0. Okay. Then alpha particle also. Alpha is also a positive particle. Then beta, it's a negative particle. Then gamma, it's a neutral particle. Then we have cations, which are also positive particle. Examples of cations are those metal ions like sodium, Na+, potassium, K+. Okay. Then we have anions. Anions are negative. Examples of anions are, we have chlorine, we have fluorine. These are all negative ions. Okay. And then we have neutral particles. We have atoms, which are neutral, like helium, hydrogen, etc. So this table is very important. So please make sure that you take this down. Okay. There are some questions in the textbook where you need this information. So this table will be really, really important for you. All right. Now let's discuss some examples on that force on a moving charge in external magnetic field. So I have a space here. So let me utilize this space. So let this be the magnetic field. Then this is the magnetic field. Now let us take a positive particle. Let this be the positive particle, and then this positive particle will be moving, okay, will be made to move. So this positive particle is moving in this direction, okay. Then magnetic field is given to you. Now let's find the direction of current. Now let's find the direction of current here. So if a positive particle is moving in this direction, then in which direction will current flow? In which direction will current flow? Remember here, my dear students, that current will also flow in the same direction. Why? Because we consider current to be a positive entity. So the direction of flow of current is considered the direction of flow of positive charge is considered the direction of current. Let me repeat this. The direction of flow of positive charge is considered the direction of flow of current. Why? Because we consider current to be a positive entity. Remember, there are two types of current we studied also. We have the electronic current and the conventional current. In the electronic current, remember the example which I just used earlier, we know that it's the electron, which is a negative charge, which moves from one terminal of the battery to the other. So we consider that in the electronic current, the movement of the negative electron is considered. But for general practice, for general purpose and for a convenient reason, what we consider is that we consider current to be moving from positive to negative, is not? We consider like that. So we consider current direction to be from positive to negative and not from negative to positive. Okay, so this is what I mean. So the direction of flow of positive particle is considered as the direction of flow of current. So current will also move in this direction. So this is the direction of current. All right. Now, then let us find the force acting on this charge. So what is the force acting on this charge? Let's find the force acting on this charge. So how do I find it? Magnetic field is given to you. Current direction has been found. So use Fleming's left-hand rule and find the direction of force acting on the positive charge, which is moving inside an external magnetic field. So let's do it. So the forefinger should point in the direction of magnetic field, which it is doing. Current direction, this is right now wrong, so let's correct it. So it has to be like this. So now current is going upwards, center finger pointing upwards, correct. Magnetic field in that direction, correct. So my thumb, which gives the direction of force, it is pointing inwards. That means the force acting on this positive particle will be inwards. So imagine that this is the positive particle. That means a force will be acting on this positive particle, which will be pushing it inside, okay, inwards. So as it travels like that, it will go inwards, okay. So it's going upward and then it's going in. It's a force acts on the charged particle, which is pushing it inwards, okay. So an inward force will act on the positive particle as it moves through this magnetic field, through this external magnetic field. I hope you got it. So the force is inwards. All right. Then let's take a negative charge now. So a negative charge is moving through the magnetic field. So the direction of movement is given to you. This arrow indicates the direction of movement of the negative particle, the negative charge. So first find the direction of current. So if the negative particle is moving upwards, then current will move in which direction? In which direction will current move? In which direction will current move? Who will give me the correct answer? I want to know in which direction will current move, okay, for regarding this negative charge. The negative charge is moving upwards, so I want to know the direction in which current will move. The correct answer is yes, the correct answer is downwards. Current will move downwards. Remember also this, my dear students, that that the direction of current is always opposite to the direction of movement of electron. See, let's go back to this example. So here I was demonstrating you. Okay, so this arrow direction, this is the conventional current. Okay, but in actual reality, the electron is moving from here to here, isn't it? So this is the movement. This is the direction of the movement of the negative particle. So the negative particle is moving in this direction. The negative particle is moving in this direction, whereas current is considered to move from this to this. So is it not opposite? Yes, it is opposite. So if the negative particle is moving like this, then current will be moving opposite to the movement of the negative particle. So the current will be moving downwards. I hope it's clear. Okay, so current direction found, magnetic field there. Let's apply Fleming's Left-Hand Rule to find the force acting on this negative particle. So let's find out the force acting on this negative particle. So let's use Fleming's Left-Hand Rule. Magnetic field, correct. Current is going down, so this has to be the orientation. Now check out the direction of thumb, because the thumb will give the direction of force acting on the negative particle. So the thumb is pointing outwards. That means the force acting on this negative particle will be outwards. Okay, so the force acting is outwards. Outwards. So what it means? So if this is the negative particle which is moving upwards in the magnetic field, then what will happen? An outward force will be acting on the negative particle. So the motion, the way the negative particle will be moving, it will look somewhat like this. Like this. So it started like this, but it's going like this. Why? Because it's experiencing a force, outward force, isn't it? Which is, so the outward push, it's experiencing a push, a force outwardly. Here it was experiencing an inward force. So the force acting on the positive particle here, it was inward. So how will it have moved? It will be moving like this. Okay, for this one, for this positive particle, if it started this journey like this, then it will go like this. Okay, for a negative particle, if it started this journey like this, then it will go like this. So the external force acting on it is, the force acting on the negative particle is an outward force. Okay, so I hope it's clear. Then what about a neutral particle? So let's take a neutral particle. So a neutral particle, so this neutral particle is moving like this. Okay, then can we find the direction of current? No. Okay, in a neutral particle we cannot find the direction of current, so there is no current flow. So no current flow here. So if there is no current flow here, then will a force act on the neutral particle? No. Since there is no current, okay, since there is no current flow, no magnetic field will be generated. So if it doesn't generate any magnetic field, then no force will act on this. So this neutral particle will just move unaffectedly. Okay, so no force will act on this neutral particle. I hope that's clear. Okay, so we'll do one more example. So now let this be the positive particle, and the positive particle is moving down. This is the direction of magnetic field. So the positive particle is moving downwards now. First thing what you do, find the direction of current. Find the direction of current. Current direction has not been given to you. Find the direction of current. Don't immediately rush to find the direction of force. Without finding the direction of current, how will you indicate the direction? How will you even find the direction of force? So you have to find the direction of current. So this is the positive particle. It's moving down. Then current direction will also be down, isn't it? Yes, because the direction of movement of the positive particle is considered the direction of current. Okay, remember. Okay, current is considered the direction of current. Okay, the direction of current is according to the direction of the movement of the positive particle. So since the positive particle is moving down, current direction will also be down, because current is considered as a positive entity. Now use Fleming's Left-Hand Rule. So current is going down. magnetic field is in that direction. So let's do. So magnetic field is correct, but my current right now is wrong, so the current has to go down. So this is the right orientation. So magnetic field, correct. Current going down, yes, current is going down. See, look at the arrow. So this is the finger which points to the direction of current. So it's going down. Then the thumb gives the direction of force acting on the charged particle. So the force acting on the charged particle will be outwards, isn't it? It's pointing towards you, it's outwards. So force acting here is outwards. That means if this is the charged particle which is moving down, then it will go like this. Again, it was moving like this. With time, it will go like this. Why? Because it's experiencing an outward force. I hope that's clear. Then yes, let's take a negative charge. And then this negative charge is moving downwards. Okay. First, find the direction of current. Indicate the direction of current. So if the charged particle, negative charged particle is moving down, then in which direction will current flow? The direction of current will be opposite to the movement of negative charge. Since the negative electron is moving downwards, current will move upwards. Remember, this is very important. So current direction will be opposite to the movement of the negative charge. So this is the direction of current. Okay, it's going upwards. Now current direction has been found. Magnetic field is here. Apply Fleming's left-hand rule and find the direction of force acting on this negative charge. So Fleming's left-hand rule. Now magnetic field, correct. I have to align the center finger along with the direction of current. The current is going upwards, so this is the right orientation. Yes or no? Or is it wrong? This is correct, is it not? This is correct. So center finger pointing up because current is going up. Magnetic field in that direction, still pointing there. Then the direction of thumb. The direction of thumb gives the direction of force acting on the particle. So the thumb is pointing inwards. So the force acting on this negative particle is inwards. Yes or no? Yes. So see, it's this easy. Okay, it's very easy. It's not difficult. So it is very easy. I hope you understood. All right. Okay. So now let's erase this and then let's do a case. A very important case. So kindly draw along with me. Draw this figure. Let us draw some magnetic fields here. 1, 2, 3, 4, and 5. 5 magnetic fields. What are these? These are magnetic fields. Then let's draw some charges. Charge number 1, charge particle number 1, which is moving perpendicular to the magnetic field. Charge number 2, which is moving at a certain angle. Then charge particle number 3, let this be the charge particle number 3, which is moving parallel to the magnetic field. Then we have another charge number 4, which is also moving parallel but opposite to the direction of magnetic field. And we have another charge number 5, which is at rest. Okay. The question is to find the magnitude of force acting on the charges. So how many charges we have? 1, 2, 3, 4, and 5. So let's find the magnitude of force acting on all these 5 charges. So first let us work for charge number 1. So in charge number 1, which is this one, the charged particle is moving perpendicular to the magnetic field. So the velocity of the charged particle is perpendicular to magnetic field. Okay. So in this case, it will experience the maximum force. Remember this, my dear students, that if the charged particle is moving perpendicular to the magnetic field, then the charged particle will experience maximum force, means the most force it will experience. All right. So here, maximum force. Maximum force. What about 2? The charged particle 2 is also moving, but it is not perpendicular to the magnetic field. So it will also experience a force, but the force will not be maximum. Okay. So remember, since velocity is not perpendicular, since it's not perpendicular to the magnetic field, it will also experience a force, but it will not be maximum force. So it will not be maximum force. So let's just write not maximum force. Then charged particle number 3, the velocity is parallel to magnetic field. So it's parallel to magnetic field. Okay. Now 4 also, even the charged particle 4, its movement is parallel to the magnetic field. So even the fourth particle, the charged particle, its velocity is movement is parallel to the magnetic field. So in this case, what happened? No force. Okay, no force. No force. Whenever the charged particle moves parallel to the magnetic field, then there will be no force acting on the charged particle. Okay, remember this. Maximum force is acted when the charged particle is moving perpendicular to the magnetic field. Okay, and a force will be acted if the charged particle is moving at some angle, okay, to the magnetic field. But if the charged particle is moving parallel to the magnetic field, whether along the magnetic field or opposite to the magnetic field, but if the movement is parallel, then no force acts on the charged particle. Remember that. Then what about this? This particle is at rest. This particle is at rest. Then again, here, my dear students, remember this, that no, but only, not no, but only a moving charge creates magnetism. Remember this, only a moving charge creates magnetism. So in order to create magnetism, the charge has to move. This charged particle number 5 is at rest. So will it create magnetism? No, that means it will not produce its own magnetism. It will not produce magnetic field. If it doesn't produce magnetic field, that means there is no interaction. Okay, so it will remain. So the force acting here will be 0. So velocity equal to 0. So no force. Okay. Now don't confuse this statement with these two. So here I wrote that only a moving charge creates magnetism. Correct. Now these two are moving, but then here what happens? Their movement is parallel to the magnetic field. So if the movement of the charged particle is parallel to the magnetic field, then at that case also no force will be acting on the charged particle, though they are moving. Remember this, though they are moving, if their movement is parallel to the magnetic field, then 0 force will be acting on them. If the charged particle doesn't move at all, then in that case also 0 force, because only a moving charge creates magnetism. And maximum force if it is moving perpendicular to the magnetic field, and a force will be acted if the charged particle is moving at some angle. I hope that's clear. Okay, so kindly write down all these points. These are very important. And then let me erase this, and then we will proceed to the last point. So let's discuss the next topic, which is force dependency for a moving charge. For a moving charge. Let's underline this. Now, you may be wondering what this is about. Force dependency for a moving charge. See, my dear students, we have been discussing about charges. We have been discussing about charges moving inside an external magnetic field. And then when a charge moves inside an external magnetic field, it experiences a force. But you have to know that there are certain factors, okay, on which the force experienced by the moving charges depend upon. So we are going to study the factors on which the force, the external force experienced by the moving charge depends. So there are three. There are altogether three. We'll discuss each of them in detail one by one. So the first point is the magnitude of charge. Now what does this mean? Magnitude means the value. So the value of charge. So basically it means this. So let's suppose that we have a 3 coulomb charge. Let's say this is a 3 coulomb charge and we have a 20 coulomb charge. So a 3 coulomb charge and a 20 coulomb charge. If both of these charges move inside an external magnetic field, let us draw a figure here for better understanding. So this is the 3 coulomb charge and this is the 20 coulomb charge. So this is the 3 coulomb charge and this is the 20 coulomb charge. So if both of these charges they move inside this external magnetic field, this is the external magnetic field, then one of them will experience maximum force, the other one will experience minimum force. Who will experience maximum force? Who will experience minimum force? Between the two, okay, I'm talking about between the two. The answer is this one. The 20 coulomb charge will experience a maximum force compared to the 3 coulomb charge. So this is the first factor, the magnitude of charge. Depending on the magnitude of charge, the charged particle will experience a force. So if the charge value is high, then the charged particle will experience more force. If the value of charged particle is less, then it will experience minimum force. I hope that's clear. So we can say that the force is directly proportional to charge. So if you want more force, then the charge should also be more. If you want less force, then the charge should also be less. Okay. Then point number 2, it's velocity of charge. Velocity of charge. Velocity of charge means the speed of the charge, the speed at which the charged particle is moving. So let's say this is a charged particle and let's say this is a charged particle. Let's keep it same size. Let's say this charged particle is moving like this and this is moving. So this is slow, this is fast. The second point is velocity of charge. So let's say this one is moving like this and let's say this one is moving faster. So who will experience more force? This one, which is moving faster, or this one, which is moving slower? The answer is, if we discuss here also, this will experience more force. Okay, if the charged particle is moving faster, then it will experience more force. If the charged particle is moving slowly, then it will experience less force. So I hope it's clear that the force acting on the charged particle also depends on the velocity at which it is traveling. Okay, so a fast moving charge experiences more force, a slow moving charge experiences less force. I hope that's clear. Then let's move to the third point, which is magnetic field strength. Magnetic field strength. FIELD, field strength. Now let's go directly to the figure for this one. So this is a slow moving charge, okay, and the charge is also, the value of charge is also less. So it will produce small magnetic field. Okay, it will produce magnetic field. Its own magnetic field will be less and it will be weak. Okay, here it's a big charge moving with great speed. Okay, so what will happen? It will produce big magnetic field. The magnetic field produced by it will be big. So the third point is magnetic field strength. So who will experience more force? This one who is producing weak magnetic field, or this one who is producing strong magnetic field? The answer is this. Okay, so this charged particle will experience more force because it is producing stronger magnetic field of its own. It is producing stronger magnetic field of its own. so it will experience more force. Okay, this is producing less magnetic field, so the counter which it receives from the external magnetic field will also be weak. Here, since by itself it is producing stronger magnetic field, the counter which it receives from the external magnetic field will also be strong. So here it will experience stronger, more force. Okay, so the force experienced by the charged particle depends on the magnetic field produced by the charged particle. So I hope it's clear. Okay, so the force is directly proportional to magnetic field, and then the force is also directly proportional to velocity. So all of this, okay, force is directly proportional to the charge, force is directly proportional to the velocity. If the velocity is high, then the force is also strong, and if the magnetic field is strong, then the force is also strong. All right, so with this, the topic has come to an end. Now, before I leave you, I'll give you a question which I want you to analyze, ponder, and give me the answer. It is on Fleming's left-hand rule. So let me write down the question, and I want you all to comment the answer in the comment box. So the question for today is: an alpha particle projected west is deflected towards north by a magnetic field. Full stop. The direction of magnetic field is, options are south, towards east, downward, or option D, upward. So this, my dear students, is the question for today. An alpha particle projected west is deflected towards north by a magnetic field. The direction of magnetic field is, you have to find the direction of magnetic field. So I want you to get me the direction of the forefinger, because this is the magnetic field. Okay, so the direction of magnetic field you have to find, is it south, east, downward, upward? So kindly give me the answer in the comment box. So thank you all, my dear students, for tuning in. So I'll conclude the video here, but I'll see you again in the next video. So stay tuned, and God bless you all.